Example number 3 will also require partial fraction decomposition, but this problem's a little bit beefier. First of all, I'll give it a scan, making sure I don't have to use long division. The degree on the top is 2, the degree on the bottom is 3, all good. No long division required. Now, the thing to spot is in the denominator, and ask yourself if you can break that up into a bunch of linear terms. So this integral, consider that it is the same as, we can factor out an x and have left behind a 2x squared plus 3x minus 2. And also we can think about factoring out our 2x squared plus 3x minus 2. And in fact, we can. If it did, it would be 2x plus or minus the number times x plus or minus the number. And in this case, we can play around with different combinations. Let's see. To get that -2, I need maybe a 2 and a 1. One of them has to be negative. Does that work? Well, let's see. This guy times that guy gives me 2x. This guy times that guy gives me another 2x. Those guys will cancel out completely. I don't want them to cancel out completely. So maybe I need this guy to be a +2 and this guy to be a -1. Let's check this out. Here's a 2x times 2. That gives me a 4x. And then -1 times x gives me a -1x. So 4x minus 1x, that gives me a 3x. Aha. That's the one I need. So sometimes you got to play around with these different combinations, right? You don't have too many to choose from, so it's probably worth your while to just write them over here on the side and see which ones work. But we have our expression where the denominator is made up of a product of a bunch of linear terms. So this guy is a candidate for partial fraction decomposition. So if I was able to use partial fraction decomposition for this term, I would be able to break it up into 3 elements. One with an x on the bottom, one with a 2x minus 1 on the bottom, and then one with an x plus 2 on the bottom. Above these guys, you would have constants a, b, and c. As before, you would try to multiply both of these sides by the LCD. In this case, the LCD is x, 2x minus 1, x plus 2. And the same on the right hand side. The left hand side is nice, short, and sweet. All of these guys cancel out with all of those guys there, leaving you behind with x squared plus 2x minus 1. When you take this LCD and distribute it to all of these 3 elements, the first product, this a over x times this LCD, the x's will be the only things canceling out, leaving you behind with a times 2x minus 1 and an x plus 2. When you take that LCD and multiply it times the second term, the 2x minus 1's cancel out, leaving you behind with a x and a x plus 2. And when you take the LCD and multiply it times the third term, you're left over with a plus c. The x plus 2's cancel out, so you'll have an x and a 2x minus 1. So I would have the left-hand side staying as x squared plus 2x minus 1. And for the right hand side, I have an ocean of terms here. Before I start combining them or doing anything special with them, let me write down what these products are for reference. This guy would give me 2x squared, and I got a 4x minus 1, so that's a 3x, and a negative 1 times a 2, that's a negative 2. For these guys, I get a x squared plus 2x, and for these guys, I get a 2x squared minus x. If I were to distribute all of these values through and combine like terms, the biggest power that I'll have on my terms would be an x squared. So I'm going to have something with an x squared, something with an x, and something with a bunch of constants at the end. When I multiply this a times this expression, I will get, for my x squared terms, 2a x squared, and I would count for that here with a 2a. When I multiply this b times these guys, I'll get a bx squared for my quadratics, and I'll account for that here. And when I multiply this c times 2x squared minus x, I'll get a 2c x squared, which I'll account for that with that 2c there, 2c x squared. I'll continue this process and look at what I get for my linear terms, things with an x. I'll have a 3ax for that guy. I'll have a 2bx for that guy. And a negative cx for that guy. For my constants, I'll have a times negative 2, negative 2a. This guy doesn't have any constants because anything I multiply that b with is going to give me an x. And in the same way, this guy will have no constants. So that's a lonely negative 2a at the end. The polynomial on the left equals the polynomial on the right. So whatever coefficients I have in front of my x squared term are going to be the same coefficients that I have on the x squared term on the left. So this tells me that 2a plus b plus 2c is equal to 1. For my linear terms, things with an x, the coefficient should equal to that 2 there. So I should have 3a plus 2b minus c is equal to 2. And finally, for my constants, they should equal to that constant on the other side. So negative 2a is equal to negative 1. So we could do this by hand. First of all, this guy gives me a little bit of insight already. I got my value of a is 1/2. And you can use that and plug it into your first and second equation. Again, your a you found to be 1/2. So you could multiply this through, and you'll have 2 plus b plus 2c is equal to 1. 3/2 plus 2b minus c is equal to 2. You can move things over to the other side and have b plus 2c is equal to negative 1. 2b minus c is equal to 1/2. And from here, you can multiply or substitute any which way you like. We can take equation 1 multiplied by negative 2, equation 2 multiplied by 1. So you got negative 2b minus 2c is equal to 2, and a 2b minus c is equal to 1/2. Add these guys together, cancel. So you got negative 3c is equal to 5/2. So c would be equal to negative 5/6. And then you can take those same equations and substitute that C into either equation to solve for that B, or you can use that same technique and try to cancel out some of these equations by multiplying by just the right expression. If I take that first equation, multiply it by 2, you would get B plus 2C is equal to -1, and 4B, excuse me, minus 2C is equal to 1. And when you add these guys together, those cancel, so you got 5B is equal to 0, or B is equal to 0. So that's one way that you can solve for A, B, and C. So again, here's my A. Here's my B, and there's my C. But there is another way you can solve this more efficiently. So we have this system of equations. And again, we can take this system of equations and convert this information into a matrix. Let me copy this down, put it downstairs. So we can take this information 2, 1, 2, 1, 3, 2, -1, 2, -2, 0, 0, -1. Again, this matrix represents that same system of equations, just carrying all the information more efficiently. And we can carry it over to our Desmos interface. And we can click on the matrix tab here. We can create a new matrix, and in this case we want a 3x4 matrix, 3 rows and 4 columns with a 2, 1, a 2, a 1, a 3, 2, -1, a 2, -2, 0, 0, -1. And we can do the reduced row echelon form of that matrix and get this answer that we can make even better by clicking on this tab here. Oh, I seem to have made a mistake on my computation. Either I put this information in wrong. Yeah, I think I made a mistake on my algebra somewhere. My A is correct, of 1/2. I might have made a mistake in my... Where did I make my mistake? I made a mistake right here. When I take 1/2 and multiply it by 2, I should have gotten a 1. So that takes things in a whole different direction, right? Hey, mistakes like this are going to happen when you're solving systems of equations. So my B and C were actually incorrect, but at least I had, my row reduced echelon form to double check my work. So I'll go ahead and trust the calculator's results here. And I get that A is equal to 1/2. My B is equal to 1/5. And my C is equal to -1/10. So these are the A's, the B's, and the C's that I needed to take my original function and convert it into these 3 fractions. So for my A, I got 1/2. For my B, I got 1/5. And for my C was -1/10. And we wanted to take the antiderivative of this guy with respect to x, so it would be equivalent to taking the antiderivative of that guy with respect to x. And this integral we can do rather trivially now. The antiderivative of 1/2 over x is 1/2 natural log absolute value of x. The antiderivative of the second term is natural log absolute value 2x minus 1 with a 1/2 in the front. Don't forget that guy. And for the last guy, -1/10 natural log absolute value x plus 2. Add a plus c, and we're all set.